Hello. In this short video, I would like to discuss wave functions and uncertainty principle. Many of you probably heard about Heisenberg's uncertainty principle, which says that average displacement in position times average displacement in momentum should be more or equal to h bar over 2. Essentially, this inequality says that we can't know exact position and exact momentum at the same time, because if our uncertainty in position goes to 0, then our uncertainty in momentum will go to infinity. In the context of classical mechanics, this really doesn't make a lot of sense. However, in context of quantum mechanics and how we think of the physical observables as the operators working on the wave function, it makes a whole lot more sense. So in quantum mechanics, we describe quantum states in terms of wave functions. Wave function can be described in terms of many different physical observables. For example, we can write wave function in terms of coordinates, right? And it would be something, let's say, this is 0, this is x-axis, this is our wave function. It could be something like this, right? And one of the postulates of the quantum mechanics says that wave function squared gives us the probability of having this value as our physical observable. So, for example, wave function with the x-axis, if it's one-dimensional space, would have like something like this. Would have a probability distribution in the area where wave function is non-zero. So probability distribution tells us how big probabilities of finding particle in certain region. For example, in this example, the largest probability of finding our particle would be in position 0, so that would be like largest p, and our probability as we're going into minus infinity or plus infinity goes to 0. But everything is fine and dandy, but in the end we still don't know the exact position of our particle. And when we think of some kind of transformations of in quantum mechanics, when we think of movement of the particle, we don't talk about some particle moving from one concrete location to another. We think of our probability shifting to one side or the other. So basically, we never know the exact position of the particle. And absolutely the same story goes to our momentum. So if we have our momentum wave function squared, we also have some kind of distribution. So now when you think of uncertainty principle, if I don't know the exact position, like pretty much ever in real life, and I don't know the exact momentum also ever, then why do we even care about this equation? Why does it matter? Because we will never know the exact displacement of the particle, and we will never know the exact momentum. Well, in some cases, our probability distributions can get really, really narrow. So theoretically speaking, we could have a distribution of displacement, which would look like this. And if we zoomed to this area, it would be like really narrow peak. Okay, right? Of course, this is absolutely a theoretical case, but in real life we definitely can get something really close to it, or there are situations where we could approximate by this case. For example, we couldn't solve Schrödinger's equation exactly for whatever the case is, but we could approximate to this Kronecker delta function. So yeah, it's called Kronecker delta, and have good enough approximation. So if we have this kind of localization, our wave function in terms of momentum will become something like this. Basically, we have equal probabilities of our momentum being pretty much anything. So if we have our particle strongly localized, we cannot tell anything about momentum. Thank you for your attention. Hopefully this video didn't suck that much.